So in this video, we are going to look in particular on channel polarization and to understand a little bit what is going on in channel polarization. So we saw that when we repeatedly apply the basic transformation, so when we generate two equivalent channels, gamma minus and gamma plus from the original channels, we get extremal channels. It means we get some channels that have a very high erasure probability close to 1 and some that are erasure probability that's close to 0. And this can be actually used to show that polar codes are capacity achieving. So what we will show is a part of this, that polar codes are capacity achieving. We will show that the fraction of channels that become perfectly reliable is equal to the capacity of the channel. When we can use them to communicate, we can communicate at capacity. So this is not yet sufficient to show that polar codes are actually capacity achieving. We need to look at the error probability after decoding. So we need to show that the error probability after decoding becomes negligibly small. This is something we are not doing because this is a little bit beyond, but in the plan to do this. Further, the proof is actually a little bit more involved if we want to. So what we have is the following situation. When we apply the basic transformation eta times, so eta applications of the basic transformation, we have 2 to the power eta different channels, and we can count, or we can write these down as gamma minus 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 up to gamma plus 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 plus. And we saw in the previous one, if gamma is large enough, the vanishing fraction will have moderate values of the mutual information, I of gamma, whatever. And all the other channels, they are either perfectly reliable, which means gamma, I of gamma will go to 1, or they are completely unreliable, meaning I of gamma will tend towards 0. So this is something that we can express also. So we can say that for every delta larger than 0, and then we count the channels that are intermediate. So we count the channels and we look at the capacity of the channels. So this is S bar is just a eta times or a sequence of eta pluses or minuses. So we're looking at all possible sequences of plus and minus of like eta. Then we're looking at the capacity or the mutual information of this channel gamma to the power S bar. And we count those channels that have a mutual information that's between delta and 1 minus delta, somewhere in the middle. And we look at this fraction, and this fraction will actually go towards 0 if eta goes to infinity. This is what we are going to show. So the formal theorem is the following. So for any binary input channel, gamma, and any a and b that are between 0 and 1, we look at the fraction of channels, I gamma, that are between 0 and a. And this is 1 minus the mutual information of the original channel. So we can make a very, very small a. So a can be very close to 0. And the fraction of channels that are between 0 and this small a, if eta becomes very large, approaches 1 minus the capacity of the original channel. Then the fraction of channels that are between A and B is equal to 0. And the fraction of channels that are between B and 1 is equal to the mutual information of the channel. Channels that have a mutual information that is close to 1, which means they are perfectly reliable, they have no error, no erasures, becomes the mutual information of the original channel. So the fraction of good channels approach the capacity of the channel. Then if we have a scheme of communicating over these channels and decoding, with what we can do with the successive cancellation decoder, then we will approach the capacity of the channel. That is channel polarization. So we're going to prove this for the binary erasure channel, and just for the binary erasure channel, just because of simplicity. So what we do is we define a new parameter of the binary erasure channel, which is closely related to the Bhattacharya parameter, but not equal. And it's the so-called ugliness of the binary erasure channel. So the ugliness is defined as square root of 4 times epsilon times 1 minus epsilon. So why is this the ugliness? Well, we have a channel with epsilon equals 0 or a channel with epsilon equals 1. These are the best possible channels for communication. If epsilon is equal to 0, we don't need to do anything. We can communicate directly because nothing will be erased. So there is no need for doing coding or anything. If epsilon is equal to 1, that's also a very nice channel because everything is erased, means we can lay back and we don't need to do anything at all because all attempts for communicating will be futile. So these are not ugly at all. So they have an ugliness of 0. And if we move in between, the channel gets more and more ugly, and we'll have this curve, this dome-like curve that's defined by the ugliness. Channel with erasure probability of 1/2, every second bit in average is erased, is maximally ugly. So regarding the ugliness, we can calculate the ugliness of our equivalent channels. So recall we have equivalent channel gamma plus that has an erasure, that's a binary erasure channel of epsilon plus equals epsilon squared. And we have a channel gamma minus, and this channel gamma minus is a binary erasure channel of erasure probability epsilon minus equal to epsilon minus epsilon squared. So now we calculate the ugliness of the channel gamma plus. Ugliness of epsilon plus is the square root of 4 times epsilon plus times 1 minus epsilon plus. And then we just insert epsilon plus. So this is 4 times epsilon squared times 1 minus epsilon squared. This is equal to the square root of, and we can write this as 4 times epsilon times 1 minus epsilon times 4 times epsilon times square root of 4 epsilon, no, sorry, epsilon times 1 plus epsilon. That's 1 minus epsilon squared is 1 minus epsilon times 1 plus epsilon. This is equal to, this is the ugliness of our original channel, epsilon times square root of epsilon times 1 plus epsilon. We take the ugliness of our original channel, multiply with this second term, square root of epsilon times 1 plus epsilon, we get the ugliness of the new channel. So now we calculate the ugliness of our channel gamma minus. Insert square root of 4 times epsilon minus times 1 minus epsilon minus. It's a little bit more involved, so it's 4 times 2 epsilon minus epsilon squared times 1 minus 2 epsilon plus epsilon squared. Okay, so the first term is 4, then we factor out an epsilon, so it's 4 epsilon times 2 minus epsilon. And this guy, this is nothing else, that's 1 minus epsilon squared. This is 1 minus epsilon squared. So now again, we rewrite this a little bit. So this is equal to 4 times epsilon times 1 minus epsilon times square root of 2 minus epsilon times 1 minus epsilon. And again, this guy is this is equal to the ugliness of the original channel epsilon times a factor, which is now square root of 2 minus epsilon times 1 minus epsilon. Okay, so now if we take the average of the uglinesses of the two new channel. So we calculate 1/2 times the ugliness of epsilon plus 1/2 times the ugliness of epsilon minus. Then we can factor out, in both cases, we can factor out the ugliness. So this is equal to the ugliness of epsilon times 1/2 times, now we have two factors. First one is this guy. So this is the square root of epsilon times 1 plus epsilon. We add plus the second term, which is the square root of 2 minus epsilon times 1 minus epsilon. Okay, so now we're looking at this first term, and we define this first term, or we rewrite this first term. We're looking at this first term in particular. The green term we denote as f of epsilon, square root of epsilon times 1 plus epsilon. And this is equal to epsilon plus epsilon squared to the power 1/2. And now we're looking at how this function behaves, how this function looks like. So we take the derivative, looking at f prime of epsilon. So this is 1/2 times epsilon plus epsilon squared of minus 1/2 times the inner derivative, which is 1 plus 2 epsilon. So this is equal to 1 plus 2 epsilon divided by the square root of 4 times epsilon 1 plus epsilon. So that's the green term. Now we're looking at the red term. So the red term, g of epsilon, is equal to square root of 2 minus epsilon times 1 minus epsilon. And we can write this after some manipulations as 2 plus 3 epsilon plus, so 2 minus 3 epsilon. So this is just factoring out everything. 2 minus 3 epsilon plus epsilon squared to the power 1/2. And we can calculate g prime of epsilon is equal to 1/2 times below we have the parentheses, so 1 minus epsilon times 2 minus epsilon, and the inner derivative is on top, so this is 2 epsilon minus 3. Okay, so now we have the, why did we do this? So we want to see, we want to bound this term. We want to get a bound of this, and for doing this, we want to find the maximum of this function. And because we're looking at this, we're looking at the extremum. How can we find the extremum? Well, the derivative must be equal to 0. So now to bound this, we're looking at when the derivative of this guys will be equal to 0. And then we find for which epsilon this is the case, and then we insert this epsilon here. So this is what we're doing. So we are calculating f prime of epsilon plus g prime of epsilon. This should be equal to 0. This is equivalent to saying that, and for this, let me just copy this to the next slide. So we duplicate this. And this was one duplication too much. And we need to go back. Just a moment. Here we go. So let me just do it in the other way. To simpler. No, once more. This. And we, I'm a little bit. So we are getting there. Go. And now we just insert the equations up. So we have everything where we want to start from. So what we do is we put those guys on a common denominator, and then we multiply those guys, and the numerator must be equal to 0. So bring this to a common numerator will be equal to 1 plus 2 epsilon. That's the square root of 1 minus epsilon times 2 minus epsilon plus 2 epsilon minus 3 times the square root of epsilon times 1 minus epsilon. And there was a there's a factor 1/2 that epsilon times 1 plus epsilon. Yes. And this must be equal to 0. And now we can factor out everything, do some manipulations. I will skip the details, but because it's very technical, and we'll find that epsilon is equal to 1/2. So for epsilon equals to 1/2, we get an extremal point, and we will just be able to insert this and then find a good bound on this. So let's take a look what happens, how this looks like. This is the situation. So we have derived the ugliness of the channel epsilon plus. We have the ugliness of the channel epsilon minus. And when we do this, when we take the average of the two channels, then we get this situation. So we have this term, and this term. Now let me check. I did something wrong. Yes. No, it's okay. Okay. So by looking at this term, so we get this expression, and we saw that we can bound this by looking at where's the maximum of this function. So it's a concave function. Looking at the maximum, find the maximum, insert, and it will lead to square root of 3/4. So epsilon equals 1/2. If we plug in epsilon equals 1/2, this guy will have 3/4, square root of 3. So plotting this will look like this. So here we have this correction term, this one, and this looks like this copular function. And you see that it's upper bounded by epsilon at square root of 3/4, which is attained for epsilon equals 1/2. Epsilon on the x-axis for epsilon equals 1/2. We are here, and we see that this square root of 3/4 just bounds this time. So if we take the ugliness of the average of the two new channels, it will be smaller or equal than the ugliness of the original channel times square root of 3/4. So the average ugliness will decrease. This is interesting. So we have an ugliness that we start from. The channel is somewhat ugly. Then we take the new channels, calculate the average ugliness, and the average ugliness will be smaller. So the channels will get less ugly on average. Okay, so now we looking at our problem. So what we'd like to show is first that the number of channels that are intermediate, this fraction goes to 0. So we'll show that the number of channels that have a mutual information between delta and 1 minus delta will go to 0. The mutual information is equal to 1 minus epsilon S bar. So this is the epsilon of the new channel. S bar is just a sequence of plus and minuses. And this is equivalent to saying that epsilon S bar is between delta and 1 minus delta because of symmetricity of the interval. Okay, so we can show that the number of channels, we're looking at the channels that are between epsilon and 1 minus delta, between delta and 1 minus delta. So we're looking at every channel. So we go over all S bar that are sequences of plus and minus to the power eta. We're looking at the indicator function if this channel sits in this interval delta 1 minus delta. And then we're looking at the fraction of those channels. And then we're saying that the limit of this is equal to 0. So instead of working with sets, which are not very useful to work with mathematically, we move our problems of a set, counting number of a set, towards indicator function. And then the next idea is we bound the indicator function. Because indicator function is also something that's not easy to work with, so we bound it. So that's what we do next. So we're looking at a bound on the indicator function. So we have the following situation. We have the indicator function. We have epsilon of epsilon s bar. And epsilon s bar should be between delta and 1 minus delta. So epsilon s bar is between delta and 1 minus delta. The indicator function will be 1. So here we have the indicator function that epsilon s bar is between delta and 1 minus delta. So this is not a function that's nice to work with. We have 0 and we have 1 over here. So what we're going to do is we're going to bound this function with a more nice looking function. We're going to do a very rough approximation. So we assume that we have a function that again looks like a copula, similar to the ugliness before. And we assume that this function f of epsilon s bar is equal to a times the square root of epsilon s bar times 1 minus epsilon s bar. So what is a? Well, how do we choose a? Well, we want the best possible approximation, so we assume that the points, they touch here. So we assume that a times and epsilon s bar should be equal to delta. Delta times 1 minus delta should be equal to 1. That means that a is equal to 1 over square root of delta times 1 minus delta. So we can say that the indicator function indicating that epsilon s bar is between delta and 1 minus delta is upper bounded as the square root of epsilon s bar times 1 minus epsilon s bar divided by delta times 1 minus delta. You see the similarity of the ugliness. So this is related to the ugliness of the channel. This is where this essentially comes from. Okay, so now we have everything at hand. So we can bound this as follows. So the indicator function indicating that x is between delta and 1 minus delta is upper bounded by the ugliness of the x, so of the argument, divided by 1 divided by square root of 4 times delta 1 minus delta. Okay, so now we can look at our sum. And this is just once more the illustration that we had previous slide. Now we're looking at our summation. So we have the following situation. So we have the indicator function at epsilon s bar is between delta and 1 minus delta. We saw this can be bounded like this. We also saw that if we take a channel epsilon s tilde and we generate new channels epsilon s tilde plus and epsilon s tilde minus, then the average of these two guys is upper bounded by the ugliness of epsilon tilde times square root 3 over 4. So this is what we have at our disposal. So now we're looking at the sum. So we want to look at this particular summation. So the sum over all the indicator functions that epsilon s tilde is between delta and 1 minus delta. So now we subdivide the sum into two sums. So instead of going over all s tilde of length eta, we go over all s. So instead of going over all s bar of length eta, we go over all s tilde of length eta minus 1, and we add either plus or minus. So s bar is equal to, here it's s bar is equal to s tilde plus or s tilde minus. So we go over these two, and then we can write this is equal to then 1/2 times the indicator function of epsilon s tilde plus the indicator function of epsilon s tilde minus. And here, of course, we take 1 out of 2 factor and move it inside the sum. And then we use our bound on this one. So this indicator function is bounded by the ugliness, and then the average of the ugliness is bounded by this guy. So this is now bounded by the sum over s tilde going from over all lengths of all sequence of lengths eta minus 1 times the ugliness of s tilde times this guy. This guy doesn't depend on s tilde, so we can move it in front of the summation. So we have reduced our summation over 2 to the power eta terms into a summation over 2 to the power eta minus 1 term. And now we can further subdivide. So now we can repeat the step multiple times. And in the end of the day, we get the following. We get the fact that this sum, if we repeat this eta times, is equal to 3 over 4 to the power eta divided by 2 times 1 over square root of 4 delta times 1 minus delta. So we look at this guy. This guy will actually go to 0 if eta goes to infinity. So this is a constant, and we have this guy that goes to 0 as eta goes to infinity, because this is between 0 and 1 with power eta, so this will be equal. So we can say, because we have bounded the sum of the indicator function, we can say that this limit will converge to 0, and we have proven our theorem. Okay, so now we know that we have a fraction of channels that polarize. So eta goes to infinity, the channels either become very good or very bad. So epsilon either goes to 0 or epsilon goes to 1. So the idea is that the encoder transmits frozen values, for instance 0, on the channels that are bad. So epsilon goes to 1. And we transmit information bits on the channels that are good. So epsilon goes to 0. And if you have a finite eta, there are some intermediate channels. They are neither good nor bad. They have some intermediate values of epsilon. Simple solution is we transmit frozen values on these channels as well. This will lead to some rate loss. How do we decode? Well, we decode the different channels using a successive cancellation decoder. And the proof can be extended also to show that actually polar codes are capacity achieving, which is something we neglected here in this very short introduction. So here is another example. So we have epsilon equals 0.5. This is the example that we just had. And we see that a big fraction of channels converges to erasure probability 1. Then the other converges to erasure probability 0. And there are some values in between. And if we increase the number of stages to 20, for instance, then we see that these intermediate ranges, they get smaller and smaller. So what we will do is we just take these channels, for instance, and transmit data over these channels. And we transmit frozen values over these channels. So the rate of the code will then be equal to, we have 1,500 useful bits divided by 4,096. So this is approximately equal to 15 divided by 40. So if we divide by 5, this is approximately equal to 3 divided by 8, which is smaller than 1/2, but it's approaching 1/2. But you see there is quite some dramatic rate loss. Of course, we could go a little bit higher here, but eventually when we reach this point, we will transmit over channels that will have erasures, and this will actually be very detrimental because in the decoder, as we'll see, will lead to error propagation. So with this, we are at the end of analyzing the channel polarization. Next, we're going to look at decoding, how to decode polar codes in detail.